Hello and welcome to this course on machine learning basics with Tensorflow. Earlier we have left in pre-processing the data, so let's continue from that part. You have to open up your Colab laboratory and make sure you click on runtime and restart on runtime and put up yes. Alright, it's working perfectly, and let's just check that it is Python 3. Let's click on change runtime type. Yes, our runtime is Python 3, and put our hardware accelerator to GPU and save it. It's allocating, connecting. Just wait for a couple of seconds. Yes, alright, it's connected. Fine. So we were pre-processing the data, and we have to inspect our first images in the first few images in the training set. So for the first, in order to inspect our first image, we have plot.figure. We are going to plot it, and to see what is there in the image of the training set, let's put plot.imshow train underscore images, and let's put the label index. Sorry, it should be a square bracket. Let's put it to 0, which is our first label, and press Ctrl Enter. I think it's peeled. Oh, fine. Just let's run all from the beginning. It should work. Alright, so our first label is, I think it's a boot or a sneaker. I'm not getting it. Maybe a boot, maybe a sneaker. It's something like that, which is there in the first label, which is indexed at 0. Alright, so let's put it in the color bar. Plt dot color bar open bracket. Alright, so if you notice, our resolution of our images is 28 cross 28. Here it is 28, here it is 28, and it is ranging from 0 to 255. So it's there, pixels values range. Alright, let's see how we can plot it in grid way. Plt.grid. Let's put the value to be true, press enter. See, we got a grid view of the image, but for the time being we're not interested, so let's put it up to false, and yeah, and let's plot.show. Press enter. Alright, that's perfect. So we have, you can scale this value of train underscore image, this label value from 0 to 9. So let's say if I put label number 2, what's the output? I think it's the pullover, and let's see for 1. I think it's a t-shirt. Alright, you can check it from 0 to 9. Fine. Now let's scale this value to a range of 0 to 1 before feeding them to a neural network model. To do so, we have to divide the values by 255, which is the pixel value range, and it is important that the training set and the testing set be pre-processed in the same way. So let's see how we can do that. Let's put up a code. Alright, so first of all, let's go for training images. Training set train underscore images equals to train underscore images space slash 255.0, and same goes for the test images. Test underscore images equals to test underscore images space slash 255.0. We're doing this in order to get the values in the range of 0 to 1. Before feeding that to the model, let's run it. Alright, perfect. So now to verify that the data is in the correct format and that you are ready to build and train the network, let's display the first 25 images from the training set and display the class name before each image. In order to do so, let's plot the figure, plot.figure, and let's put the figure size to be using fig size equals to, and let it to be 10, 10. Fine. And we want the first 25 images, so we'll use a loop for I in range 20, I in range 25. We are going to plot dot sub plot subplot 5, 5, comma I plus 1 and plot dot xticks closing bracket, plot dot yticks and let's put the grid value to be false. Plot dot grid, let's put it as false, and yeah, plot dot imshow. We're going to put train underscore images with train underscore images with the value I and comma cmap equals to plot dot cm dot binary and plot dot hex label class underscore names, and let's put the class name that was trains label train class underscore names and square bracket train underscore labels train underscore labels this I. Let's close this one. Have we closed it perfectly? Yes, that's done. And plot dot show, plot dot show. All right. So you can see we are our first 25 images. First is ankle boot, t-shirt top, then dress, t-shirt top, pullover, sneaker, pullover, sandal, and so on. There are like 25 images. We have our first 25 images, coat, bag, and all. You can just check out whether our first 25 images are the same or not. Alright, it's same, it's going to be the same. Fine. So now we have already pre-processed our model. We have verified the data that's in the correct format, and our figure size is 10 by 10. Alright, fine. So now let's start building the model. So building the neural network requires configuring the layers of the model, then compiling the model. So let's first set up our layers. The basic building block of neural network is the layer. Layer extract representation from data fed into them. and let's hope these representations are meaningful for the problem at the hand. Most of the deep learning consists of chaining together simple layers. Okay, so most layers, such as let's say keras dot layers dot dense, have parameters that are learned during training. So let's see, let's create a dense layer. Fine, so let's first declare model equals to keras dot sequential, and alright, inside the sequential we are going to put it up. Fine, so first puts the keras dot layers layer. First we are going to use flatten layer, flatten A. Alright, what does this tf.keras.layers flatten does? It's like first we are it's the first layer in our network, and it's going to transform the format of the images from a two-dimensional array. If you remember, we have a array which is of 28 cross 28 pixels, the dimensional array, to a one-dimensional array of 28 into 28, that's going to be 784 pixels. You can think of this layer as like unstacking rows of pixel in the images and lining them up. And this layer has no parameters to learn, it only reformats the data. Okay, it's just going to flatten up, it's as simple as that. And we are going to flatten the input shape, so let's put the input underscore shape, and which is going to be equals to 28 comma 28, so 28 comma 28, and let's put a comma outside, come down. Next we are going to put a dense layer, so for putting a dense layer, type keras dot layers dot dense, and which were in this dense layer will be having 128 neurons that are nodes, and we will be putting up an activation function, and this activation function is going to be the ReLU activation function. ReLU. Alright. In case if you're not aware of this terms of ReLU functions and all, I think you should go for a course that's there in Coursera by Andrew Ng. That's the deeplearning.ai. Another great course is by Stanford University. They have a very good theoretical concepts, and you will get all the things pretty much clear. This is just a hands-on of implementing those things. So if you are very much new to this, first you should clear those up. Alright, and let's put another layer, which is going to be our output layer, keras.layer dot dense layer. That's going to be, sorry, layers dot dense, keras dot layer dot dense, and let's put done. I will explain it what I'm doing over here, and let's put the activation function equal to softmax. So softmax, and yeah, that is it. Alright, fine. So let's see, after our pixels are flattened, the network consists of sequence of two layers. First is our dense layer. These are densely connected, means that's a fully connected neural layer, and the first dense layer has 128 nodes or neurons, and the second, that is the last layer, this one, second layer is the 10 nodes, has 10 nodes. So you can see I have declared nodes over here. Here we have 128 nodes, here we have 10 nodes, and this 10 nodes is a softmax layer that returns an array of 10 probability scores that sums up to be 1. So whenever you want a score in terms of probability, you are going to use softmax function, and each node contains a score that indicates the probability that the current image belongs to one of the 10 classes we have. So alright, let's run it. Great. Now let's compile our model. We'll build our model. Let's compile our model. So before the model is ready for training, it needs a few more settings. These are added during the model's compile step. So we'll be dealing with loss function, optimizer, and metrics. So in case loss function is like the measure how accurate the model is during training, and you want to minimize the function to steer the model in the right direction. Optimizer is that how the model is updated based on the data it sees and its loss function, and metrics is like used to monitor the training and testing steps. In our code, we'll be using accuracy, the fraction of the images that are correctly classified. So let's see how we can do that. For that, let's put model.compile, and let's put our optimizer function, optimizer is equals to, so we are going to use Adam optimizer, and comma, let's put loss equals to, so we'll put sparse categorical cross entropy as our loss function, sparse underscore categorical underscore cross entropy. So we have defined our loss function, and remaining is the matrix. So let's put our matrix equals to that is going to be accuracy, alright, let's run it. Fine, now our model is compiled. So now let's train the model. So training the model, our neural network model requires some steps. First of all, we'll be feeding the training data to the model. In the shown exercises, we are the training data, which is labeled as train underscore images and train underscore label arrays, and our model will learn to associate images and label. We are going to ask the model to make prediction about a test set in this example, which is our test underscore images array, and verify that the prediction match the label from test underscore label in the array. Alright, to start our training, we call model fit method. So it is called model fit because it fits the model to the training data. So let's call our model.fit method. Let's click on a code, model.fit. We're going to fit our train underscore images, and then train underscore labels, train underscore labels, then, and we are going to put epochs is like how many round of trainings you want. So we are going to put epochs equal to 10. So that means our 60,000 data which is there in the training images will be like trained for 10 times. So it's comes out to be some 6 lakhs, I think. All right, you can it's up to you, like if you want to put epochs as 5, if you want to train the data for the 5 times, 7 times, 8 times, 10 times, it's up to you. But let's, for this example, let the epochs be 10. Let's press Ctrl Enter, and here we will see the loss and accuracy metrics. If you see, it is being displayed over here. Our loss is 0.4942, accuracy is 0.82, like loss is 49%, accuracy is 82%. So let's see up till 10 epochs. So you can see the metrics over here. It's the last epoch remaining. Alright, so we can see we have got an accuracy of 91% in our training images. Let's evaluate the accuracy with our test images. Let's see how our model performs with our test data set. Okay, so in order to do that, we are going to put up new code table. So let's do test underscore loss comma test underscore accuracy equals to model dot evaluate, and it's going to evaluate test images, test underscore images comma test underscore levels, images comma test underscore labels, and we're going to put the verbose equals to, let's put verbose as 2. All right, and we are going to test for accuracy. So let's see, let's put a print function, print let's put /n test accuracy that we have is for test underscore ACC, test underscore ACC. Now let's come on this one. So we are getting a test accuracy of 0.88, that is around 88%, but we can see it's like a little less than compared to the training. In training we got around 91%, in testing we are getting around 88%. So this gap between training accuracy and test accuracy represents overfitting. Overfitting in a machine learning model, like is a worst case, and it's like it remembers the previously unseen inputs that's on the training data, and so we have to avoid that overfitting because it remembers all the data it's seen. So we have to, and when it sees an unseen input that's on the, so well, we'll be doing a follow-up with convolutions, neural network and all, where we'll be getting a much more good result in terms of accuracy. So we have learned how to build our model, how to set up our layers, how to compile the model, how to train the model, and how to evaluate accuracy. And last, let's make predictions with the models that we have trained. We can use it to make predictions about some images. So let's make some predictions. So in order to do prediction, let me put predictions equals to model dot predict, and we are going to predict our test images. Test underscore images. Let's press Ctrl Enter. All right, so let's see our first prediction. Predictions of the level 0. Alright, here the model has predicted the label for each image in the testing sets. Let's look at the first prediction. And by the way, a prediction is an array of 10 numbers. They represent the model's confidence that the image corresponds to each of the 10 different articles of clothing that we have, and you can see which level has the highest confidence. So let's see which has the highest confidence using argmax function np.argment max of predictions 0. Predictions of class 0. Alright, so the model is most confident that this image is an ankle boot, which is a class name 9. Examining the test level shows that this classification is almost correct. So let's see the test level. Let's see test underscore labels of 0. Yes, that's 9. So yep, we have done our prediction, and you can do much more. You can plot this up in the graph, the predictions in the graph, and also you can check whether the predictions are correct or not with the labels. Fine. And you can also plot several images for the prediction. That I'm not going to cover because it's going to be more lengthy. So in the next tutorial we'll be looking on some another use cases. So stay tuned, and thank you very much.